Yes, so as announced yesterday, today we will talk about inflation and the cosmological perturbation. We have already seen one reason why we need to introduce inflation. This is connected to the particle horizon we discussed yesterday. The fact that you have that the particle horizon grows with time, so you see more and more regions which were not in causal contact before. So in that sense, you have to find an explanation why you see an homogeneous, for example, cosmic microwave background temperature in all directions, even if these regions were not in causal contact before the time we really measured them. There are another couple of problems that are connected to, which are solved by inflation, and which plague, in some sense, the standard cosmology, and in practice also connected to the fact that the acceleration is actually negative. And the other problem, the only one I would like to mention a little bit, is the flatness problem. So the flatness problem is why do we measure today that the total omega is practically 1, so that the density of the universe, if you want, is practically the critical density, as I defined yesterday. So the issue is why now omega total is practically 1. And as we didn't describe the Friedmann equation in this setting, but if you remember, the Friedmann equation was this one yesterday. Gn over 8 pi. No, sorry, the j pi is on the top. Yes, so. And practically this equation you can rewrite, if you want, in a relatively simple form once you divide by h squared, which is exactly the factor which gives you the, if you want, the critical density. So if you divide everything by h squared, yes, here you can put an h squared here. You see that this one is 1, because h squared over h squared is 1. This here, this combination h squared dividing a pi gn, is exactly what I yesterday defined as a critical density. And this one is an additional term, but you see you have 1. This is the, if you want, rho divided by rho critical, and this is the curvature term. So it should be clear that if this term, which if you sum over all densities is exactly omega total, is equal to 1, then k has to be equal to 0. So then automatically you have that if the total energy of the universe in units of the critical density is 1, you have a flat universe. So this equation you can also write in the more compact form as k over a squared h squared. And this term here is sometimes also called omega k, if you want. And therefore, the fact that omega total is very near to 1 is directly connected to the spatial curvature. The question is, what is the evolution of the spatial curvature? So if you want, what happens if you take the derivative of, well, I will take the derivative of omega total minus 1. The derivative of omega total minus 1, you can easily compute it through the equations we considered yesterday, and it actually related to the equation for the acceleration. So indeed you find here 2a double dot over ah times again omega total minus 1. Okay? So I hope you recognize this type of equation. You have a first ordered differential equation proportional to the same variable but multiplied with something here which can have a sign, positive or negative. Now it should be clear, as long as a double second is negative, this is a positive coefficient. This means that the omega total minus 1, with the time flowing, it's actually deviating from 1. Okay? If it is not equal to 1, of course, omega total equal to 1 is exactly a fixed point of the equation. But if omega total is larger than 1, if this is positive, it's going to grow. If omega total is less than 1, this is positive, this will become negative, so it's actually going to decrease.
But are you assuming that A is a constant? Or?
No, I don't need to assume. It's just a matter of the sign. That is important information. Of course, this is depending on time. In principle, a double second is a time dependent, so this will not be a constant, but nevertheless, behavior is exactly the same. As long as this sign doesn't change, the overall behavior is the one I described. So it should be clear, therefore, that if you start with a cosmology with a particular value of omega, so let me say this is exactly 1. So we start with whatever value of omega you want to have. Then in principle, if you have a double dot negative, what happens is that the omega will go further away from 1. Okay? So this means that you have to start really very, very tuned equal to 1 or exactly equal to 1 in order to explain why now we still have omega total practically 1. Okay? Now it should be clear that there is a simple way to actually turn around this argument or turn around the behavior, and this is changing the sign of a double dot. Okay? Should be clear if I do the opposite. So if I have a double dot positive, then you have a minus sign here, and then the behavior is exactly the opposite. Omega total equal to 1 is actually, if you want, an attractor solution. So in that case, whatever initial condition you start with, you will flow towards omega total equal to 1. Okay? So in that sense there, you're not more so sensitive on the initial conditions, and you can drive the system to something very near to 1, so that now, even if in the last period of evolution of the universe, of course, we had a negative a double dot, so we were actually going away from 1, still we are not able to go so far away to have a value that we can measure in that sense. Okay, so it's clear, as I said before, the omega total is of order 1 with an error now which is less than 5%. So of course we don't know if it is exactly 1, but it is still very, very near to 1. Okay, and therefore again, this is again another argument that tells you that there should have been a period at the beginning of the cosmological evolution where the second derivative of the scale factor was positive. So we had accelerated expansion. And of course this expansion had to last long enough to bring omega from the natural value, which of course we don't know exactly what it was, but so much near to 1 that now even the subsequent evolution did not bring it far away from 1.
So can I ask?
Yes.
The contribution of dark energy is in omega tot?
It's in an omega total, yes. Dark energy is also another energy density, so it's just a constant energy density, but I consider it as an energy density. So omega total, of course, is the sum of all contribution to ρ. You will have a cosmological constant, you will have dark matter, you will have baryons, you will have radiation, everything is in ρ. Okay, if you want, I can write here ρ total.
But I asked that because I thought that this K is the thing that distinguishes between the Sitter universe or anti-de Sitter.
No, no, no. K is connected to the spatial curvature. So K decides if the three-dimensional space is curved, a positive curvature, negative curvature, or zero curvature. It has nothing to do with the ADS or DS. Okay. This is connected to the sign of the cosmological constant, which is indeed in the ρ inside. Okay, you could have in principle de Sitter or anti-de Sitter also with positive or negative curvature if you want.
Sorry.
Yes.
Do you see a combination between these two ones? For example, at first A double dot is minus, but somehow after that it becomes positive.
Yeah, then of course it will change from one behavior to the other. But in some sense we know that in the latter epoch of the universe, so in the sense as I explained yesterday, the normal type of matter we know of, so radiation, or if you want non-relativistic matter, will always give you an A double dot negative. This is because the pressure is positive. You remember the A double dot equation was proportional to 1 minus 3W, I think. What was it? 1 plus 3W, sorry. Okay? So as long as the equation of state is larger than minus 1/3, you have always negative acceleration. And therefore now we will look instead to an epoch of the universe, or a type of energy, which will give us positive acceleration. So W will be much more negative than minus 1/3. Okay, so this is indeed the key point. The matter that dominated the expansion of the universe in the recent epoch, of course nowadays one has to admit it's actually dominated by dark energy, whose W is probably around -1. So in that sense we are accelerating again now. So in that sense you are correct. We had if you want, you had a phase of acceleration, a phase of deceleration, and now we are going into another phase of acceleration. But the phase of acceleration we have now was too short, so it's a very short phase. The equality between the matter and the cosmological constant happened at a z of around 1/3 or something like that. This means that there is no time really to solve this problem with the late acceleration of the universe. Okay, so this, yes, there is another question there.
Are there any cosmological models where you set this 1 minus omega exactly to 0, and then maybe it's protected by a symmetry or something? Will it always stay at 0?
Well, of course, you don't need to do much, because from the classical point of view, if you have omega total equal to 1, it is a stable solution. I mean, not stable, it's a solution. It's, of course, depending on the sign of A double dot, it can be, as I said, either an attractor or instead the opposite. But it's omega total is, of course, all the energy density of the universe. So I don't know of any model which is able to predict it. Also because you remember there is always also the component which is the cosmological constant, and we are not able to say why the cosmological constant must have a particular value. So in that sense it's always, I mean, I don't know of any model which can tell you exactly what value omega total should have, just because we don't even know how to compute or to predict the cosmological constant. Okay, so this one is one problem we have that we can solve again, changing the evolution of the universe. There are other couple of problems that people were very worried about in the past, in the old days. Now probably we don't care so much anymore. One problem was the relics. Of course, if you have a grand unified theory and you break a group which has a U1 subgroup or some other subgroup such that you produce strings or monopoles and things like that, you are also worried that you don't produce too many of these objects, because usually if they are too many, they would dominate the energy density of the universe, and they have again a behavior, they give a cosmology which is not the correct one. Okay? In particular also they are topological defects, for example, like monopoles. They are really incredibly massive, so you really don't want to have such a huge energy density in topological objects. And so this one was a problem, and actually was the original reason why GATT in the old days proposed inflation to, in some sense, dilute away the topological defects. And the other problem people had in the old days was also the problem of entropy, which is perhaps not so easy to explain, but the idea is just that if we compute the entropy that we have now, it's actually not so low. And if we go back in the past, of course, the density, so the volume of the universe becomes smaller. So the total entropy, if you look at the adiabatic expansion, it actually giving a very large value, just because the present entropy is not very small. And if you go to smaller volume, you immediately have at the end that the entropy density grows. And in the old days it was, and it still is, a little bit puzzling to have a universe which generated from a singularity at 0 size, but it already contains a huge amount of entropy. And this is because usually in this idea, we were considering, of course, entropy production during most of the cosmological evolution. Nowadays, we are probably not so much worried about the entropy because there are processes in the universe or in the cosmological evolution which can produce entropy. For example, just a simple particle decaying out of equilibrium. Or, for example, and this is the thing that we will get perhaps to at the end, is the end of inflation. So the decay of the inflaton or the also non-perturbative generation of radiation at the end of inflation. Okay, but this one is again an additional mechanism you have always to keep your mind to, that the inflaton at the end, and we'll see it later, will have to reproduce the thermal universe, and in that sense it will have to produce sufficient entropy to give you back the thermal bath. Okay, so I am already practically going on top of myself because I practically already gave you the solution of all these problems. The solution of these problems is to have an epoch of inflation. And epoch of inflation, as I said, it's an epoch which in principle at the beginning you could just think, okay, I just need to have a double dot to be positive. So you need a W relatively small, but not perhaps -1. Actually, at the end, it turns out that the easiest way to generate is really to get something which with W near to -1. And this one you can actually see immediately. In that case, you have actually a long sustaining expansion, and it is also an exponential expansion. So let me review the issue about, so if W is equal to -1, this means that you have actually a cosmological constant. Indeed, if you plug this W -1 in the continuity equation we had yesterday, we had, this one was practically 3h rho 1 plus W. Okay? So you see immediately, if W is -1, this is exactly 0. So W equal to -1 implies that d rho in dt is 0. Okay? And if the rho is constant, so then I can plug it in the equation for the Hubble parameter. Sorry, I think I forgot a 3 here. Yes. So I call it here, this one, rho lambda, to be on the safe side. So this is exactly a cosmological constant density. It is constant. So it should be clear that then I have immediately also a solution of this equation. H squared is A dot over A squared. So I can just write that A dot over A is equal to the square root of this quantity. And then this equation, of course, has directly a solution. The solution is nothing else as an exponential. Of course, here I'm choosing a plus sign. In principle, you have also the minus sign solution. But generically, if you want a positive acceleration, well, the acceleration is actually equal. But yeah, you have usually the growing solution. Okay? So this one is the solution, or if you write it, you can write it also as e to the plus ht. So this is the scale factor. Okay? So you have an exponential growth of the scale factor. This, of course, has a positive, if you derive it as a positive acceleration. And it gives you exactly the behavior as you see here also for the for the omega total minus 1, that it tends to drive omega total minus 1 to 0. And you see that this one would be practically what we want, but there is one reason why this simple thing doesn't really work at the end. Perhaps you can already see it. What is the problem of taking a cosmological constant to give you an inflationary phase?
It never stops.
Exactly, it never stops. This one would be exactly at the Sitter solution, and you would never go out of it because the density is constant, it remains constant. Also, all the other densities of matter or radiation will be diluted away, so they will become even smaller than they were at the beginning. So they will never actually gain and the dominance over the cosmological constant. So you will practically end up in the Sitter phase. The universe will become empty, nothing will be there. Okay, so that's not a good solution. So it should be clear now what we want to achieve. So we need a cosmological constant which stays only for a certain time. So we need a kind of dynamical cosmological constant. And the issue is now, how can we realize it? Now, luckily, we have one very simple type of field which can give us quite easily a cosmological constant, as I will show you in a minute. And this is a scalar field, a classical scalar field. So we can just look at what happens if I have a classical scalar field. Okay, I will take it for being complete also real, so I don't have to worry about any sign. Of course, today we have seen it already, what a scalar field is, so I don't need to say much about what the action is. Of course, the only difference is that I will be in GR, so I have here a square root of minus G, where minus G is the determinant of the metric. And then I will have the usual Lagrangian, which I can write with a kinetic term and a potential. Okay? Now, once I have this expression, it's actually pretty easy to derive what is the energy momentum tensor of a scalar field. The general expression for the energy momentum tensor, you have to do the variation with respect to the metric. And it is just the derivative of the Lagrangian on the field, the kinetic term, minus G mu nu, the Lagrangian itself. Okay? And now we can check if this energy momentum tensor looks in any way similar to the perfect fluid I was discussing yesterday, for example. Now we can immediately see what is T00. T00 will be practically, if I do here the same indices and I will get a D0 phi, D0 phi, and then I will have the minus the G00, which is just 1, the Lagrangian. So this one will give me nothing else as the derivative 1/2 actually. Derivative square, I will have plus 1/2 the gradient term square plus the potential. So this should not be surprising. This is just the Hamiltonian or the Hamiltonian density of the scalar field, as it should be. Then I can go and look at the II component, and here no sum over I, and here I have a similar thing, minus minus plus L, and in this case I guess I get again D0 phi squared. Well, wait a second, I think there is a minus sign there. Yes, there is a minus sign, sorry, I forgot. There is a plus 1/2, no, sorry, minus 1/2 gradient of phi square minus V of phi. Let me check, sorry. Minus plus, yeah. And then, of course, I have the off-diagonal pieces. If I go to the T0I, it should be clear the metric is 0. So the only piece I have is d0 phi, the I phi, which is practically the derivative of the scalar field times the gradient. And then I have Tij with I different from j. And this is again is twice the gradient. Okay? So we see immediately that the scalar field does not really look like a perfect fluid. Indeed, we have off-diagonal pieces in the energy momentum tensor. On the other hand, these pieces always depend on the gradients. This means that if I am in a region where the gradients are small, where I can neglect the gradients of the scalar field, so that means an homogeneous scalar field, then of course these ones would practically be negligible. Okay? And at the same time, this was also I can also drop the gradient piece in the energy and in the other diagonal component, and I get exactly out something which looks very much like the perfect fluid. Yes?
Shouldn't there be contributions from the scale factor? I mean, like for example, for the G mu times L, shouldn't there be like
no. No, we don't have contribution. We have G mu nu. G mu nu you have to use. Ah, the A square you mean.
Yeah.
Sorry, yes, of course, yes. Here you have the, yeah. Yes, sorry, you have it, but I don't care about them because the spatial part I will all put to 0. So it's indeed, here you will have A. No, this one not actually. It's in this term, so it will be only. Well, you will have it because also here, in principle, you have to take care of the metric. Yeah, you could have it in front of the gradient, but I don't care about them because the gradient is at the end what I want actually to be 0. Okay, so. The important thing is the kinetic energy coming from the time derivative and the potential, and on this term for sure I don't have any A square term. So this means that if you have a homogeneous scalar field, then I have practically the following expression. I have an expression for the density, the energy density, which is B just this one. Or I can write it as phi dot square plus the potential. And if you remember, the diagonal part of the energy momentum tensor is the pressure with a minus sign. So in this case, the pressure will be just be the derivative of the inflaton minus the potential. So you see that in this case, for example, for a homogeneous scalar field, it's a field which doesn't have a constant W. The W, which is the ratio of the pressure divided by the density, can change in time, and this is exactly what we will exploit. And in particular, it will go from -1 when the potential dominates to +1 when the kinetic energy dominates. So this means here I have always the W of the scalar field will be always between -1 and 1, and it will be possible to have a regime where this is practically -1 as long as I have the kinetic energy or the phi dot to be very, very small compared to the potential. Okay? And this is nothing else as the slow roll, what is called the slow roll regime. where phi dot square is much less than the potential. And in that case, here I have a factor of 2, but it's not so in this case, then I have effectively a cosmological constant. Notice that if this is small, then the field moves very, very slowly. This means also the potential will be practically constant because the field doesn't move very much. So the value of the potential at a particular place is a constant. So I have automatically something which self-sustains itself. Moreover, we will see that we will have also another condition, we will see it in a minute, connected to the second derivative of the field, because in the differential equation, of course, for the field, there will be also the second derivative. So the idea then should be clear. I need a field, scalar field, such that I can be in this slower regime with very, very small kinetic term. And then for a while, I will have the potential dominates the energy density of the universe. I will have my exponential expansion, like in the sitter. Then at the end, I want actually the field to pick up speed. And at a certain point, the kinetic energy will not be negligible anymore. And I will stop inflating. Okay? And this one is practically the basic idea of inflation. Notice that at the moment, I didn't tell you anything about the potential. At the end, we will see in a minute, the potential has to be of particular shape in order to be able to sustain this type of cosmological evolution for sufficiently long. Okay? Now, for what regards the classical evolution of the field, you can just now write down also the equations of motion. The equations for the scale factor are exactly the same as the ones we had yesterday, just with a cosmological constant, or if you want, with a scalar field in it. And moreover, we have, of course, an equation for the scalar field. So we have the dynamics is given by the equation I wrote already. So h squared is nothing else as 8 pi gn over 3. And this is the density of the scalar field, which is 1/2 phi dot square plus v of phi. Let me use the same phi. Okay? And then in principle, I would have the equation for the acceleration, which I actually can write is on an equation for h dot. H dot is nothing else as a double dot over a minus h squared. And if you substitute the equation of yesterday, you find minus 4 pi gn phi dot square. And in this case, again, you see immediately that the fact that if I choose phi dot to be small, then automatically h dot will be practically 0, so that I have really a constant h. And then, of course, the other thing which is missing is the equation for the field. And this is nothing else as the Klein-Gordon equation, but in an expanding universe. So in this case, indeed, we will have an additional contribution with a 3h phi dot plus v prime of phi is equal to 0. Okay? So this one is indeed the contribution coming from the fact that we have a non-trivial metric, and the v prime is the usual condition of having a displaced field from the minimum of the potential. Now, let me discuss briefly just the simplest case you can think of, and this is just a simple massive free field. So I can take, for example, the potential to be just a mass term. Now it should be clear that in this case, I can directly write down the expansion there as the equation as a phi double dot plus 3h phi dot plus m squared phi. So this equation should be well known to everybody. Especially we have a mass term, so we have nothing else as a classical harmonic oscillator with a constant mass. The friction here is in principle not constant. It would depend on time, but as long as I have the case where the h dot is very small, h will also be constant. So I can actually treat it as being h constant, m square constant. And in that case, of course, everybody knows the solution, I hope. It is nothing else as the same, it's a harmonic oscillator with friction, and in some cases actually the friction dominates on the mass. This is exactly what we will need also later on. So if you can, you can write the solution, of course, as the usual form with an exponential ansatz, and then you can compute what is the exponential, and you find two solutions as usual. So this is the solution. So you see immediately that you have, again, two solutions. Generically, you expect to have at least the first term is always negative. The second term, since there is a difference in sign in two squares, it's always smaller than the first term. So both, if you want, of the exponents are actually negative. See, this means that in some sense, yeah, well, we'll see in a second. Of course, here, as I said, I will be interested in a regime where h square is larger than m, and then I can do an expansion and find two solutions. One is exactly minus 3h plus what was it? Well, let me read it so not to have it exactly wrong. Plus 1/3 m square over h square, and the other solution is practically minus 1/3 m square over h square. I'm going only to first order in m square over h square. Now it should be clear now what happens. This is exactly what I have to plug in the exponential. So you see immediately one term has a very strong decreasing exponential. The other term instead has a pretty small negative exponential. This what this means is that this solution, the solution with the large negative exponential, will actually disappear very quickly, because this is nothing else as a function which goes to 0 in a time which is 1 over h. Instead, for a long time, the only thing which will remain is the second solution, which is a solution which has an exponent, so it will be 5. This is exactly the slow roll solution. Indeed, this is the one who has the smallest kinetic term as well, which is a some coefficient m square over h square t. So at the end, I start with a second order differential equation, which as usual has two solutions. But in the long time, the first solution just goes to 0, and I am left only with the second solution, which is indeed what is called the slow roll solution. And actually, I could have gotten it immediately. How could I have gotten that immediately? Well, I could have exactly thought about.
Excuse me.
Yes.
But here it should be m squared over h, not h squared.
Sorry, yes, it's over h. Yes, you're correct. Sorry. Yeah, you would have an ht otherwise, yeah. Sorry, yes, the units otherwise are not correct. So how could I have gotten the second solution immediately? Well, I could have said, as before, let me assume that the field is going very, very slowly, and I don't want it to pick up speed. So this means I want actually that the second derivative of the field should be actually smaller than the first derivative of the field, so that I can actually assume that the slow rolling is actually sufficiently long in time. Now if I have in this regime, then what I can do in this equation, I can again completely drop the second derivative, because this is practically 0. And I have immediately the solution that phi dot is equal to minus m square over 3h phi. Okay, this is what is usually called the slow roll approximation. or slow roll solution. Well, I don't write the solution because it should be clear. The solution is exactly this one. Okay? Of course, if I do it in this form, I can also assume that h is not constant, and then I have the real solution, which means that phi of t is actually the coefficient e minus the integral in dt of m squared over 3h. Okay? So in that sense, here I can also take into account the fact that h is not exactly constant. Okay. And as you see, then I have practically two conditions for having this type of solution. Which are related to the first and second derivative of the field. I want the first derivative of the field to be much smaller than the potential, because I want to neglect the kinetic energy in the energy density of the universe, and I want also to be able to neglect the change in the Hubble parameter. And secondly, to use this solution, or if you want to forget about the second solution of the second order differential equation, I need also that the second order derivative of phi is less than the 3h phi dot term in the equation. Now these two conditions you can actually rephrase in terms of the potential. And this is because, of course, as I said, from this solution you see immediately that you get, if you write the full potential, this will tell me that v dot is minus v prime over 3h. So if you want, you have a relation between phi dot and v prime. And then if you take a derivative, you see that you are connected then to the second derivative of the potential. So you can rephrase these two conditions into condition just on the potential. And these are usually written in terms of the slow roll parameter epsilon and eta. Epsilon is v prime over v squared and has to be much less than 1. And eta is equal to m Planck squared, the second derivative of the potential. And also this one in modulus has to be much less than 1. And these two conditions are just a condition telling you that the potential has to be sufficiently flat, because these are conditions on the first and second derivative of the potential. And in that sense, you don't care what kind of potential you have. The important thing is that the first and second derivatives over the potential have to be small enough. Okay, so now in principle I can solve everything. So if you give me a potential, I can plug it in, I can check if it is good enough to have inflation. I can compute the evolution by integrating the slow roll equation there. And I can do practically everything related to the background evolution. So I'm not going to do it explicitly. Actually, it could be a good exercise to give, to take also this m square phi square potential and compute exactly what exactly the behavior is. I actually can just draw you the diagram in the phase space. So if you look at phi dot and phi, especially for the simple model with the m square phi square potential, you have practically two regimes where you have the slow roll condition satisfied. So these one are exactly the conditions where the phi dot is, sorry, it's actually depending on phi, so it's not really a constant line. But it's I wanted just to show it's a, yeah, so it is actually a straight line in some sense, which goes there, and a straight line which goes here. And what happens is that if you start with a different type of solution, due to the exponential practically behavior of the second solution, you will actually have the velocity decrease very quickly to go exactly along the slow roll trajectory. Okay? And the same thing if you are on the positive field or negative field, doesn't matter. You remember the equation was phi dot is equal to minus m squared over 3h phi. Okay, that was the slow, that is the straight line if you want. Then of course at a certain point you will reach the region where the velocity becomes to be such that you start to actually see the deviation from the slow roll trajectory, and in particular you will end up at the end around the minimum of the potential. So in this case I am assuming the minimum of course is in 0, and around 0 you will have a spiral behavior which goes towards the minimum. So practically the idea in the looking at that from the potential point of view, you start up here. If you start with too fast velocity, you slow down due to the e to the minus ht contribution, which then it slows it down. So here it could be also fast rolling. Then you have a regime where you go to slow rolling. And in this epoch, you will have inflation. And then you will end up again fast rolling because the potential will become smaller in this case. And then at the end, you will also have oscillations around the minimum of the potential before the field stops at the minimum. Of course, the energy density it contains, it has to be get rid of before, in some sense, it stops. And in this epoch, it will actually decay or produce radiation and additional fields, so that you will actually transfer the energy density from the inflaton to a thermal bath. Okay? Notice that the only slight problem with this m square phi square potential is just that if you look at the region where the field is slow rolling, if you look at the fact that you need v prime over v square to be small in Planck units, you see immediately that the condition is of the following type. V prime is nothing else as m square phi. The potential in this case is nothing as 1/2 m square phi square. So you see that here you completely lose the dependence on the mass, but what you obtain is that the field has to be sufficiently large. This has to be much less than 1, so the field has to be sufficiently large with respect to the Planck scale. So this is typical for these polynomial inflationary models. Usually you have the epoch of inflation at values of the field which are a few times the Planck scale. You can change the potential if you want. You can take another polynomial, but you see that when you derive whatever polynomial you have only 1 power less in the numerator, and this means m Planck over phi has to be small. Okay? And indeed, one has to admit that these also have another problem with the cosmological perturbation, which we will come to in a minute. Okay, so I hope that the idea is clear. It's important to know that first you have this attractor kind of behavior at the beginning, so that even if you start in another point in the parameter space or in the phase space with, for example, large velocity or smaller velocity, you are actually driven towards the slow roll trajectory. Then you stay for quite a while along the slow roll trajectory, and then later on you end up instead oscillating around the minimum and getting rid of the energy density of the inflaton to radiation and the normal thermal bath. Okay, so this one is the background evolution, but of course this is not all, and actually the most interesting part comes now. The fact that actually on top of this classical and homogeneous field evolution, we also have in principle quantum fluctuations. Okay? So this is the thing we will discuss next. So add quantum fluctuations. So generically, as in all field theories, I can write my field as a classical field, or in this case I will take homogeneous. So this is exactly the field I was discussing until now, plus a fluctuation, which does depend on space and time. So it doesn't have to be homogeneous. And it is, in principle, the only requirement, of course, it is much smaller than the field itself. So I can treat it as a fluctuation on the classical scalar field. And in this case, of course, I can write also an equation. I can try to derive, of course, the equation also for the fluctuation. And at the end, it's not very much different from the equation I raised for the scalar field. So first of all, in the case of the of the quantum field, of course, I can go in Fourier space, since it is space dependent. And so I will have a delta phi with a particular value of k, which is the momentum. It will be the comoving momentum. We will get there in a minute. If we write the equation for the fluctuation, we find that an equation which is very similar to the one for the homogeneous part. It's clear it's a linear equation, so it should be actually pretty much the same. Then I have, nevertheless, the gradient part. Sorry, I have a minus the 1 over a square. So here I have the a 1 over a square. Sorry, I forgot it before, I guess. And then I have, as usual, in this case, I don't have the first derivative of the potential, because I assume that the, as I said, that the that is practically contributing to the classical field. I have only the second derivative of the potential computed at the classical field times my fluctuation. Okay? So the idea is that the first derivative of the potential sets the dynamic of the classical field. If you want, the quantum fluctuation of a field are always computed around a zero, so minimum or maximum of the potential, so where the first derivative, if you want, it's vanishing. So in this case, therefore, I have just the second derivative of the potential, which is practically, if you want, in the case we had before, this will be just nothing else as an m square, so it will give me exactly the similar term of what I had before. But for a generic potential, of course, this could be also depending on other terms.
The gradients are taken with respect to the background, or?
The gradients are taken with respect to the, this is the physical gradient, is the with respect to the distance. And indeed
You take the gradient of the background or of the...
No, sorry, the perturbation. Ah, sorry, I forgot. I write it differently, so let me see. Let me say that phi is this background and this curly phi is the fluctuation. Yeah. And now what I can do is to go to conformal time. So yesterday we saw we can go from t to eta, and we can go to Fourier space, so that I will have here a k in comoving momenta. And so comoving momenta, because the physical momenta will be k over a, where k will be my comoving momenta. So in some sense you can think of, I will just take out the dependence on the scale factor from the momentum. And then I get the following equation. Wait, sorry, I have another change of variable. It's a bit longer. Where did I left the eraser? Ah, here. Sorry, the other thing I can do, which also simplify my job, is to define a new field which is just a rescaled scalar field. So I will define the fluctuation in k multiplied by the scale factor in a conformal time, if you want. Okay, so I'm just taking out a factor of a, And this is I do because there I will get rid actually of this 3h delta phi dot. So this will actually disappear. And this brings me again to a very simpler equation. So if I write the equation for u of k, I have then I will take also, as I said, the conformal time. So I will use the prime to be the derivative in conformal time. And this gets rid also of in part of this 3h. So I will have the second derivative of u of k. I will have no linear term in the first derivative. And then I have just k square plus the mass term. So the w, well, let me write it here as a explicit second derivative on the classical field. So this one is the mass term. And then I will have an additional piece which comes from rewriting this 3h piece, which is the a double dot over a. Now, it should be not surprising, since again I have a linear equation, and I have a linear equation which I am assuming that the perturbation is small, so I can always linearize the equations, that I get out something which looks again like a harmonic oscillator. If you want, here in this case you can look at it as a quantum harmonic oscillator, but you have again here the usual k-square dependence. But what you have here is that all of these in principle could be like some kind of mass. But of course, this is not constant. Okay? I have an a double dot over a. This is, for example, in the case of de Sitter, I know actually how to compute it. So for de Sitter, I have that I can do the relation between time and conformal time, and I have practically that the eta variable. Yeah, so the eta variable is -1 over AH. Okay, H will be constant, but A will be exponentially growing. So eta is practically something which goes from -infinity to 0. And if you want, you can rewrite it as with the exponential. So it's e to the minus ht over h, if you want to have the relation to the time. And then if you compute the a double dot over a, then you see immediately that, of course, here you have a of eta is equal -1 over h eta. So if you do the second derivative, you obtain that what you get out is a 2 over eta squared. Or if you want, you can rewrite it as h square a square. Okay? So this means that what you have is a field with a time-dependent mass. Okay? And this, of course, will give you, and actually the important point is also, you see it here, it's a negative sign. This means here is a square and you have a negative sign. So it should not be surprising that one of the solutions we will get, it's a solution of growing solution. Okay? Because a negative sign in the mass gives you, if you would be in de Sitter, in Minkowski, so assume we are not in Minkowski, and you have a negative mass, constant, the solution will be an exponential. Okay? Instead of having an oscillating function, you would have a growing exponential and a decreasing exponential. In this case, we have also the expansion of the universe, so the solution is not actually growing exponentially. It will grow only as a power law, or it will grow like a, the scale factor. So I'm not going to, well, I'm going to sketch the solution, but not to. So the behavior is the following. You see immediately that you have, as long as k square is larger than the AH, okay, then what happens is that you have a positive mass or a positive frequency, and you have an oscillatory mode, okay, as usual. So as long as k is larger than AH, the solution is oscillatory. It's oscillatory in conformal time, but nevertheless it's oscillatory. Now, the point is though that A is growing. It's exponentially growing. So with the time passing, A will grow, and at a certain point, AH will be larger than K. And when AH is larger than K, then what dominates this equation is the last piece with a negative contribution, if you want a negative mass. So then the mode will not be oscillating anymore. There will be a growing mode and a decreasing mode, as usual. Okay? And due to the fact that A is time dependent, every mode will start to be with k squared larger, and then we'll end up, or not everybody, but most of them will end up with k smaller. So for every mode, I will have a behavior which, and every mode then will grow at a different time, because of course this equality of k equal to AH will happen at different times for different modes. Okay? And the solution, if you want, I can also write it in the second case. So for a k much lesser than AH, you can find easily that U of k has a solution of this type. You have a growing solution which is nothing else as A itself. You can see it immediately here. If I can drop this one and this one, I have exactly U double dot k over U of k is equal to A double dot over A. Or double prime, sorry, not double dot. Okay, so this has to be a solution as long as I can neglect these two pieces. And then I have the decreasing solution, which is actually proportional to eta, which is decreasing. So it's actually a 1 over h, a, something like that. And therefore, as you probably can immediately guess, even in this case, I can in some sense forget the decreasing solution because it will go to 0 pretty quickly. And what I'm left is only the growing solution, ck of A. And when you look at the scalar field, the original one, you remember we define it to be A times delta k was U of k, which is ck of A. So I can actually drop the A, and what I have as a solution is that my scalar field will be constant. Okay? Now why I introduced this U of k? There are two reasons. One reason is, of course, the equation is simpler, and I have no first derivative in the field. The other is also because usually what we quantize is actually U of k and not delta phi of k. Why we do quantize U of k? Well, actually, we do quantize it because we have exactly this growing solution. And having this growing solution is showing us that this is start with a quantum fluctuation, but when you grow in the amplitude of the fluctuation, you grow also the occupation number of the fluctuation. Remember, this is nothing else as an harmonic oscillator. And the occupation number, if you want, is nothing else as a combination of these coefficients of the Fourier modes with their coarse creation and annihilation operators. Now, if I have a large occupation number, this means that this field will behave at the end when I have a large occupation number, like a classical field. Okay? So I know this is a bit difficult to swallow, and I must admit there is no real proof or mathematical expression that I can give you that really tells you that this field becomes a classical field. But the fact that this is as I said, this becomes a field with a large occupation number, after in some sense it becomes grown and it goes out of the horizon, this condition k equal to AH is often called the horizon condition. then I can treat the field as a classical field. And this also has the advantage that then I can just embed it into GR, because GR, as we all know, it's just a classical theory. And in principle, the question would be, how can I, with a classical field, sorry, with a quantum field, generate a classical fluctuation in the metric? And this is exactly the way it happens. So it's a quantum field in what is called usually also squeezed state, which is also, squeezed states are often common in optics, where you have a large number of photons, for example, in lasers, and there you can practically define a classical field with the field or the superposition of all this large number of photons. Yes?
These modes are growing. Do you always satisfy the condition that delta phi is less than the background?
Sorry?
If these modes are growing, do you always satisfy the condition that the perturbation is less than the background?
Well, yes, in the field I do, because this is a constant. So U of k is not my original fluctuation. The fluctuation, if I rewrite it, the solution in the fluctuation will get to a constant. And this constant, actually I didn't say what the constant is. The constant you have to fix by the initial conditions, of course. And this usually is fixed by assuming that you are in the Bunch-Davis vacuum, as it's called. So you take the positive energy solution and you match it with a Minkowski type of wave function. So in C of k, you will have both a dependence on k and a dependence of the Hubble parameter. But delta phi of k can remain sufficiently small. It does remain sufficiently small as in the regime we are interested in, even if the U of k is growing like the scale factor.
But if the perturbations don't grow, how does the argument with the high occupation number work?
Well, as I said, the argument with the high occupation number works for U of k, not for delta phi of k. That's why we quantize U of k and not delta phi. Yeah. Well, you could argue that you can't quantize whatever you want, but of course it's also important, if you want, that the equation has this form, because this form is the one which you can more directly relate it to the harmonic oscillator, like for example in the usual quantum mechanics. Okay? So if you want, you can also write the Lagrangian and just look at the momentum and the potential. And in some sense, in order to have an harmonic oscillator, a quantum harmonic oscillator, you want the usual p square over 2m plus 1/2 k x square. Okay? And this type of form of the Hamiltonian you can obtain only for the U of k and not for delta phi. Okay, so but let me get to the other picture. Because the important thing, which perhaps is not so clear here yet, is the issue about the dependence on k. Because here we have practically that the growth of the function starts exactly when k is equal to AH, or opposite if you want, since it's A which depends on time. And you have therefore that in some sense for every mode, you in some sense fix the condition at this horizon exit. So the idea is practically the following. We have here on this axis we draw the scale factor or the logarithm of the scale factor. And in the other axis we draw the scales. Okay, I will try to draw physical scales. For example, also length scales for the particular k value. Now, the other important quantity I need to plot in this plot is of course the Hubble parameter. The Hubble parameter is also sets a scale, and you see here AH sets also the scale of the horizon exit. So here we have in practice the Hubble parameter during inflation, which will be practically constant. And then after inflation, the Hubble parameter, sorry, this is Hubble to the -1 actually, because the Hubble parameters start to decrease after inflation when you go to radiation dominance or matter dominance. But in this case, since I plot h -1, it will actually start to grow. And it will have different slopes depending on radiation dominance. So here you will be in radiation, and here will be in matter. And I am assuming this point is the end of inflation. So A end. Okay? And now we can plot on this plot what happens for a physical scale. Now remember, a physical scale, K is not a physical momentum. It's K over A, the physical momentum. This means that the physical scale is something like 1 over K times A. Okay? So the physical scale grows, is stretched, like we expect, because space is stretched and also the physical scale is stretched. So we start with the physical scales, which are very small, which are well below h to the minus 1, so within the horizon. And in this regime is exactly the oscillatory regime. So here in this epoch we have oscillations. Okay? Then we reach this point is the point where we have exactly K equal to AH. So here practically the fluctuation, the U of K starts to grow. But on the other hand, if I look at it as, sorry, here I'm taking it a little bit too, I have to a little bit flatter if I want to go in there again. If I look at the delta phi will be constant if I go out of the horizon. So after just few short time after, I can assume here that delta phi k is frozen, as it's called, or is constant. And this will stay out. And in principle, one fluctuation can remain all the way out of the horizon until today. But of course, I have also fluctuations which are a different k, which starts later. They will go out of the horizon later, and then be frozen again outside, and then they can come back. Sorry, this should be a straight line, but I'm not very good at drawing it. So let me try to redo it. Yes, so I have to do the curves a bit flatter. Or do this one a bit steeper. That's the other choice. So I have again a fluctuation going down out. Here again it is frozen when it is outside the horizon. But then at a certain point, since the horizon will catch up, because h to the minus 1 starts growing, you will have again an epoch where the fluctuation is again equal to the horizon and will come back. Okay? When it comes back, it's exactly, as I said, it becomes in some sense a classical fluctuation already when it is outside the horizon, and here it will come back as a classical perturbation in GR. Okay? And as you see here, different scales will come back at different times. Okay? So the fluctuation go out continuously. I have any fluctuation will go out at different time during inflation, and will come back at different time in the cosmological evolution later on. Okay? And these fluctuations are those which will be, and we will actually try to do it now, to see how this fluctuation then you can translate into a fluctuation of the metric, and in particular of the curvature. Okay? So yeah, so but all of them behave in the same way as constant when they are outside of the horizon. And the other important point, as I said, is that the initial condition, of course, is set when the scale is much smaller than the size of the horizon or of the Hubble parameter. So in this regime, you can assume that you are practically in a Minkowski vacuum, if you want. Or actually what people call a Bunch-Davies vacuum, which is the real vacuum for a de Sitter case, but which correspond to the same condition in the limit of practically zero wavelength to the Minkowski case. Okay. And of course, the last thing I want to say before going into the cosmological perturbation is, as I said, you have to fix this constant by the initial condition, and it should be also clear that this is a field, so you should have a scale something like dimension of energy. So the only thing which can give you a size of this fluctuation in a de Sitter space is of course h. Okay? So the fluctuation of the scalar field at the end will be of the size of the Hubble during inflation. And this is the size of the fluctuation at that time. And depending on the Hubble parameter, you will have larger or smaller fluctuations. Okay, so the prediction is here. Now, notice that I have to admit, first of all, these equations I wrote, they are simplified equations, okay? They are not the full equations. In reality, of course, the Hubble parameter is not exactly constant. There is a mass term, this derivative of the potential, which I am just dropping. I did drop. So in practice, if you take also all that into account, you can do it systematically in the slow roll approximation. And this brings you correction which are proportional to the slow roll parameter epsilon and eta. So the solution which I gave you, it's up to correction of that order. So it's still okay, but it's not the full correction. So you can do better. You can do first or even second order in slow roll if you want. But nevertheless, it gives you at least the idea of how things work. And so I didn't want to give you the full expression, but you can find it in quite a number of references. And in particular, I forgot also to give you references even yesterday. There are a few couple of TASI lectures which are pretty good on inflation and cosmology. One by Jim Klein of last year's TASI, and an older one of Baumann about inflation, which where you can find all the formulas and all the details. And generically, just to give you at least the punchline, as I said, the fluctuation of the field at the end of the day gives you a power spectrum. So the 2-point function, if you compute the vacuum expectation value of two fields fluctuation, which is of the order of h squared over 4 pi. Remember, I have here rescaled the k's so that the k actually drops. So usually the power spectrum is defined as k cubed times the usual power spectrum, or I don't know how you call it. There are different ways of calling it. So this means that if you do the integral in decay, you have directly, in this case, the decay times this quantity to have the integral in the k variable, okay? Because I am already taking away a k cube factor. And if you want to get the full result, so here you have the h square, which you can relate to the potential during inflation, of course. So it should be also clear that then you can translate it in the curvature perturbation. So I give you the result now, and then we will do the computation. You find something of this type. And you have the v cube divided by v prime squared at the time of horizon exit. Okay? So now how can you set the time of horizon exit? You have to solve the whole evolution of inflation and to see when a particular scale crosses the horizon. So depending on the dependence of t of a. And you have then to evaluate the corresponding field value, and at that field value you compute the potential and the first derivative of the potential. Okay? If you want to have an instruction how to do it, we can discuss it in private, since it is it is just a bit long but not very difficult. Now, these are fluctuations in the field. I said and promised you that actually this fluctuation you can translate it into fluctuation in the metric. And indeed, if you want to compute the cosmological perturbation, you need to do the expansion also of the metric. So one perturbation is the field perturbation, but we also have a metric perturbation. So we have a delta G mu nu. And delta G mu nu, again, will depend both on space and time, so it doesn't have to contain only the scale factor as we have in the normal background metric. Now, of course, you have to classify what kind of fluctuation you can have. And indeed, we should already know how many degrees of freedom we have in the metric. 10, exactly. We have 10 degrees of freedom. And then we can classify them according to how they transform under a rotation, for example. And we find that there are 4 fluctuations which are scalar fluctuation. We have 4 fluctuations which are vector fluctuation, and 2 fluctuations which transform as tensor fluctuations. And if you want, I can write you also the expressions. So G00 will give you one of the scalar perturbation. You can write it as 2a square big phi, which is actually usually also the, if you want, the Newtonian potential in GR. Then you have, of course, the 0I component. The 0I component contains both a scalar fluctuation and a vector fluctuation. You can write it with a gradient of a scalar function plus a vector function. And then you have the Gij, which has a more complicated expression and contains a tensor, vector, and scalar fluctuation. You have a psi scalar fluctuation, a E scalar fluctuation, a F vector fluctuation, djfi, and then you have the true tensor fluctuation, ij. Okay? Here you have some additional constraints, of course, because here in some sense I already extracted the gradient part, so I have actually that the gradient of S and the gradient of, what was it? Yes, and the gradient of F also are 0. And at the same time, also for the tensor perturbation Aij, I also have the condition, this is of course traceless, because I am extracting already the trace, if you want. And it has also transverse as well. So you have Aii is equal to 0, and also the gradient of Aij is equal to 0, and it's of course symmetric as well. Okay? Now, I have now these equations, and in principle I have to do the first order perturbation equations, so the Einstein equation at first order in the perturbation, and of course also the field perturbations as well at first order. But the field perturbation is more or less similar to what I showed you before. So what we can look at are the Einstein's equation. And, well, sorry, there is another thing I have to discuss. Of course, all these fluctuations are not all physical fluctuation. Why not? Because we have a freedom. We have a kind of gauge freedom also in gravity. We can do a diffeomorphism transformation in the coordinates, which means practically just a shift in the coordinates. And this is something we can do locally, is a local transformation. So we have, as usual, we can change the coordinate to x mu prime, which is equal to the old x mu plus a delta psi mu of x. Okay? So I have here a shift of the coordinates, and it should be clear, here I have 4 components, so I have 4 fields I can shift with. And these 4 components allow me exactly to put to 0 4 of the fields I have here. In particular, you can show this one, of course, there are 2 scalar and 2 vector. It should be clear because it's exactly the same if you want as G00, G0I. You can rewrite xi again as two scalar functions and one vector with which is transverse. So we can use the xi mu to absorb away two scalars and one vector perturbation. Okay, so usually, traditionally, you take away the B and the E, okay, and you leave the phi and the psi, and you take away one, either the SI or the F, and then you are left, in principle, with two scalar perturbation, 2 degrees of freedom in the vector perturbation, and 2 degrees of freedom in the tensor perturbation. The vector perturbations are usually not excited by inflation. Why? Because you don't have a particular direction. Okay, the inflaton field is homogeneous. What you do is actually you produce a scalar perturbation like d phi, and you produce actually also the H field, because in some sense this is nothing else as a free field. Okay, on the metric. So in that sense, therefore, we can actually forget about the vector perturbations. So the second vector perturbation Okay, so at the end, therefore, we can write down the equations for the, I will write just those for the scalar perturbation. Actually, for the tensor perturbation, the equation is even simpler. It's just a free field equation, because there is no other tensor around, or no other, as long as you don't have a background which produces a quadruple, you don't get a source of those fields. So let me, very good, I destroyed. Okay, I will just write down the equation and we can then discuss them tomorrow in case. So from the Einstein equations in conformal time, because this is in this case is important. You get that the Laplacian of psi perturbation, you have the Hubble in conformal time, which I write it as H curly H, with a psi prime plus H, the phi perturbation, is equal to 4 pi Gn A square the delta T00. Then I have an off-diagonal piece and then I have the long equation, which is the ij part. Sorry, here I forgot a delta ij, and then I have a minus a 1/2 di dj of phi minus psi is equal to, again, the energy momentum tensor ij component. Okay? So it should be clear that now I have to compute this end change or the fluctuation on the energy momentum tensor, for example, for the scalar field or for whatever other energy momentum tensor I have after inflation. And in generically, as I said, for the scalar fluctuation, you have two fluctuations, phi and psi. But you see, for example, from this equation, if you take I different from j, and you have a energy momentum tensor with no off-diagonal pieces, which is actually what it is in the case of the, or at least this is small in the case of inflation. This you can, sorry, here also you have usually the average of this tensor. Then you can actually conclude that the phi fluctuation and the psi fluctuation are equal, up to constants, etc., which you don't really need to take into account. And then you are reduced to one fluctuation in the gravitational sector plus the inflaton. So at the end, what comes out is that you can write a combination of all these three scalar fluctuations, which is the one which is really interesting. And it is the curvature perturbation, which has also the advantage of being gauge invariant. So this one is explained very well in the book by Mukhanov, if you are interested. And you have a gauge invariant combination. And this gauge invariant combination is exactly equal to, well, it's often called V, at least by Mukhanov. And this is the fluctuation in the field plus the phi fluctuation, the big phi. And this is also up to a factor of A, the fluctuation in the Ricci scalar, in the three-dimensional Ricci scalar. So in that sense, this is exactly what is also called the curvature perturbation. And you have then the second perturbation, which is yeah, usually the second perturbation is not as important as this perturbation. So, and you see here you have both the inflaton field and the phi in the combination. So it's practically not so difficult in some cases to consider the phi field during inflation and then translate it into the curvature perturbation, which is instead the thing which is more important after inflation, where you re-enter the horizon in this region here. It should be clear that in this region here, in this epoch, the inflaton is not there anymore. You don't know, it has decayed, it's disappeared. So the only thing which remains is the fluctuation in the metric, which is the curvature perturbation. Okay? Now I am already over time, so I'm stopping here. Of course, there is still one thing missing. What is missing? Well, we'll discuss tomorrow. Well, we have still to see what happens to the fluctuation when it re-enters the horizon. Okay? So it should be clear that this is also something you can explore. In that case, what you will see is that the fluctuation grows. Okay? Not always, not in all epoch of the universe. Actually, it depends on what is the dominant component of the energy density of the universe. We will see it tomorrow. But these, in some sense, that you produce during inflation are the initial perturbation, but then they evolve after they re-enter the horizon, and they end up into temperature fluctuation of the CMB, or later on also in the fluctuation in the large-scale structure, really. So clusters, galaxies, and all the structure that we see in the universe, the idea is it all was created because we had the initial condition from inflation. Okay, if you start with a universe with no fluctuation, you will have a universe with no structure. Okay? And I think I will conclude here. And tomorrow we will look at this last step and then go back to look instead at the thermal universe and dark matter. Yes?
Did you say that the polynomial inflaton potentials, they have a second problem in the context of these perturbations?
Yes, sorry, I forgot. Okay, yes, this perhaps we could also discuss tomorrow. Of course, the power spectrum that you produce during inflation will also then produce the anisotropy, the spectrum of the anisotropy that we measure in the CMB. And from that, we can actually measure, for example, the spectral index, which is the dependence in K. So due to the fact that here the different K come out at a different time, and H is not exactly constant, is constant but not exactly, you expect to have a dependence on K, which is proportional actually to the slow roll parameters. So you can predict how the decay dependence should go given a potential. And what turns out is that the value of the spectral index, which is measured by the CMB, and also the value of the tensor to scalar ratio, it's actually not in accordance with what is predicted by the usual polynomial models. So lambda phi to the fourth or m square phi square are excluded. You need, I think, still allowed is something like linear potential and something with a square root potential, which is a bit funny. But in principle, of course, you can solve the equations if you want also for a square root potential. Yeah.
What do you mean by average of the energy momentum? I mean, it should be just the perturbation. I mean, what average over what?
It's the perturbation, but here again, there is always the issue. You have to average it of on a particular. How you call it? So you start always with something which is quantum, and you want to translate into a classical quantity. So you need to do a kind of average of the on the realizations if you want. So I can try to be more explicit tomorrow on this, but it's. Yeah, so it's always the usual problem that if you start with a quantum field, you would need to, in some sense, to take a expectation value of this quantity and then have a kind of, you have to assume that the ensemble average is similar to the, so the average of the usual quantum average is similar to a kind of ensemble average. And this is again the usual problem we have in cosmology that the only thing you can really measure are the statistical properties, but you cannot really measure a single realization if you want of the universe. This is also connected to the
later universe. If you would take an average, this would be like a spatial average. No, so this is
yes, exactly.
This would be like quantum average or something, right?
Well, it's not always clear because later on you will use these also for a fluid in the.
Sure, but then if you average, you don't have a space dependence anymore. This is first order perturbations, right? So this would just be zero, the average over perturbations in later universe.
Well, you mean you would not have a k. Here I am not looking at the k, so the k is still here. So I'm not looking at the k dependence of t.
Yeah, but there's spatial dependence.
Yes, there could be, yes. More questions? Okay, I don't see any, so I think we can close here for today. And as I said, tomorrow I will catch up with the last part. Thank you.